Hello everyone, so this is Jacob Beerhorse. We are doing the bonus project here. So we're going to be using Fluent. We're going to be testing different Reynolds numbers across a flow over a cylinder, and we're going to plot the coefficient of pressure against the distance across the x-axis, and since it is a cylinder, we are going to be relating it to the degrees. Okay, so to start, we're going to use the geometry in the mesh that we did in project 3. I'm just going to show you that real quick. Hello. Hello. Thank you. Okay, so it started with creating a cylinder or circle. On your XY plane, I chose 5 centimeters, and then you wanted to create a rectangular shape around it. So that way you can cover and simulate the flow within it. So I've made this about 5 centimeters. I wanted this to be a large vertical height, so there was no squeezing over the flow, because that could create problems with your coefficient of pressure, which I had problems with earlier. But creating a large area for it to go over really helps with this project. And then you're going to generate a concept, create a surfaces from sketch, apply it to that rectangular figure. So then the mesh you can use for all cases, as you can see here. Good. So with the mesh, first thing you have to create is your method. Okay, once you apply that method, you want to put it to the body. Okay, and then you create some sizing. I did about every 5 centimeters. I created some sizing, generate, and then you go to refinement. I refined it up to about 3, and you generate, and your overall mesh looks something like this. Okay. And now throughout the project, just like other projects, you need to name the edges so that way you can relate them when you're running your setup. So I have the inlet, symmetry, outlet, and then the wall, which we are going to be taking the coefficient of pressures on, as you will see later. So now we can go into our setup. Okay. So while that loads, the first case we want for the Achenbeck is going to be a Reynolds number of 1 times 10 to the 5. So what I did here is pull out my calculator, and you can either change the flow velocity or you can change the viscosity to get your target's Reynolds number, because your density and your diameter of your cylinder is going to remain constant. Okay, so I'm going to use, as you're going to see, I'm going to use 5 meters per second for the flow for each case. And to calculate that Reynolds number it wants me to find, I'm going then to divide by the Reynolds number, and that gives you the viscosity needed. So for this first case, with my parameters, I'm going to have 3 times 10 to the negative 6. It's going to be our target viscosity. Okay, so just like many other projects, you're going to go materials. Once it loads, I'm going to close this mesh geometry. Hopefully things can run a little faster. All right, so materials, let's go to the air. This is where you can put your target viscosity to help you reach that certain Reynolds number. As you can see here, put it at 1.2, select it to 3 times 10 to the negative 6 to get that first target viscosity, change, create, close. Boundary conditions, these are going to be the same for almost every case. You're just going to put it at 5 meters per second here. Apply, close. Now, go to our reference values here. I like to make sure the viscosity is what we want. Now, your length of 1 meter, depth of 1 meter, density check, and then your area is just the area of your cylinder that you're going to be going over, which is going to be that circular cross-sectional face. Pi over 4 times your diameter squared. For mine, I get 0.019635. Now, I want to run this from the inlet, reference zone, surface body. Okay. First case should be okay. We're going to initialize. Now, run the calculation. Now, you can do 500, and if you're not getting the values that you want to see, bump it up to maybe 1,000. Can get some better results in that way. Okay, we're done. Awesome. Now, you want to hop over to your plots. Run the XY plot. It's going to be your pressure, coefficient of pressure, direction vector, wall, save plot. Now, if you did this right, you should see that it's going to start at 1, should not exceed -3, and then it's going to end. Most cases I see ending around -0.5 until you run your in viscous case. You will see different. So now you have your plot. Good. Now we're going to write this to file. You're going to okay. Close. I haven't created a plot yet for that, so go to the one you already created. I'm sorry. Write to file. Write. And then I like to put it in my downloads. There's many places you can put this, but it's easy for me to find. RE, case 1, zoom. Okay. Now you're gonna hop over to your Excel. Hope you can see this. Okay, and we're going to insert. No, you're gonna go to data, get data from your text CSV file. Now my downloads, I can search it up. Already case 1 zoom, and there she is. Open. Okay, load. Awesome. Now I'm going to come back. We need to get the other cases before we come back and create our overall chart. So back to the workbench. Now we go to solution 2. While that loads, we're going to be getting a 2.6 times 10 to the 5 case now. Right? Let's have our licenses. Okay, so while that happens, I can now find which target viscosity I'm going to want for this case. Do the same process in your calculator. Okay, I'm going to want a viscosity around 1.1538 to the -6. Just follow suit here. Let's go check your air properties. I got my density. There it is, my viscosity I'm going to be using for case 2. Change, create, close. Okay, boundary conditions. Okay, well, oh yeah, it's inlet. Awesome. Values, make sure everything's right. Boom, 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 boom. Awesome. My inlet, please. Eyes. Down. For me, please. Thank you. Awesome. 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 We go to our plots. Export plots. Awesome. Save plot graphics. Starts at 1. doesn't exceed 3. Good. Write to file. Write. Jake. Downloads. Yeah, case 2. Zoom. Okay. Thank you. We go back to our Excel. Okay. Now we're going to insert data. Text CVC. Downloads. RE. Case 2. There it is. Open. Thank you. Thank you, sir. Okay. So now you got case 1, case 2. Okay. Now we go to our solution 3 now. Just keep going. We got 3 more cases to go. Okay. Again, while that's going, again, as it goes every time, you can kind of just check to make sure it's following some type of pattern here. Checking both these cases, they did look pretty good so far. So we'll keep working. Okay, so while that goes on, let's figure out what our third one should be. Sure it's a little higher this time. Yep, so we want 8.5 times 10 to the 6. Okay, we get 3.529 into the negative 8. Go to our models. Oh, not that. Ah, fluid, air, 1.2, 2.5294 to negative 7. Okay, my bad. So it's 8.5 times 10 to the 5. Okay, good. Good, good, good. So now we have the right one to the negative 7, as you can see here. Good, very good. Close. Boundary. Inlet. 5 ms. Awesome. Close. Reference values. Bang, bang. Awesome. Specified inlet. Awesome. Initialize. Run me calculation. Okay. That was pretty quick. Okay. Plots. XY plots. Please give me. Oh, whoa. Coefficient direction vector. Let's plot. Graphics. 1. Awesome. Doesn't exceed the negative 3. Awesome. Papers. Right to file. Right. Take your downloads. These 3. Okay. Top over. It's there. Data. From a text. RE. 3. Awesome. 2 more. I don't know if I mentioned it, but when you're doing these, you can you're using the same geometry and mesh, so you can share it. Makes your life a lot easier. So take that from me. Okay. They got us. No licenses. Close. You. Okay, so when I run into this problem, I actually close other applications and seems to work. So yes, right. Yes, yes. Ta-da! See? It's magic. Okay. So materials. Fluid. Air. Now, if I'm correct, we want 3.6 times 10 to the 6. It's going to be a fairly small Reynolds. I think it's going to be 8.3 times 10 to the 8 or something like that. Oh, right. 8.3 times 10 to the negative 8. Amazing. Close. Boundaries. Set to 5. Thank you. Close. Run my calc. Calculate. That was quick. Thank you very much. XY plot. Created. Oh, save plot. Open. 1. Does it exceed negative 3? No. Compare. Hovers around negative 2 point. That looks good. Good. Write to file. Write. Jake. Downloads. Yeah. All right. Now we just have error last case. Okay. Now, our last case. We're going to get our inviscid flow. Alright, so this one's a little different from all the other ones, where we are actually setting a viscosity for this bad boy. I don't even know what that means. I've never seen that before. Okay. It's a nice looking mesh. Okay. So then we're going to go to general. We're gonna go to models. Viscous. And here this is where we turn off our usually you'd be at K epsilon 2, but for this case you're going to get inviscid. Okay. So that makes this easy. You're not going to have to set a viscosity this time. You can see. Awesome. Change create clues. And boundary conditions. I don't want to set the same. I don't know what's going on here. Why can I not open that? Boom. Apply 5. Awesome. Keep perfect values. Go double check it. Give it to me from the in. One, two. Awesome, 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 awesome. Let's try that later. We should be good. Now, theoretically, this envisage should start at 1, should be our lowest dropping one to about -3, and then it should taper off to 1 again. But I've noticed from multiple trials, something seems to not be extremely accurate at the end. It's going to taper off at about like 0.5. It is higher than all the cases, the previous ones, so I'm assuming it is doing something right. But what we can check is that it is the lowest corresponding one. Awesome. Does it start at 1? Drops off to about -3. Awesome. And then, like I said, it comes up to about like 0.5. Not mistaken. Awesome. Okay, so now you have all your data. Now we are going to transform it because for some reason Fluent likes to give back some numbers that the Excel chart cannot understand. So very importantly, you're going to have to convert these two numbers or else your plot will look crazy. Come. Okay, so see. Virtual number. Okay. See? That's very important. Didn't convert. You're paying sometimes, guys. That's not good. Awesome. 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 Okay. Now we go to case. Almost. It's not to be lazy. Oh, all right. Now we can do the fun part. Okay, so I'm gonna create this inviscid model first. I think I'm mentioned. So, couple things you're gonna have to do first. Okay. So let's just do. So this is going to be this. This distance because we are in centimeters. So as you should see, it should start at the beginning of my cylinder, which would be negative 0.025, and it ends at the end of the cylinder, 0.025. Those corresponding radians would be 0 degrees at the beginning, 180 degrees once you make it to the end. Okay, awesome. Glad we clarified this. Okay. Now we can, so you want to select your data. This is how you help name your lines, so you can be very clear to the grader. Where did you go? Okay. All right, so now we're going to need to insert our other parameters. So this one, we're going to have this RE 1 minus 10 5. Okay. Well, what X values do we want? We want our distances on the axis. Thank you. Now we want lines. Very much. Okay. Just make sure everything's going okay over here. Awesome. Good. Just do that for the other three. Set that at 82.6. 10. Oh, pain, pain. We will probably do that once or twice. I didn't do it twice, did I? Big amount of What? Me. Oh, 3s. I don't trust that, so I'm gonna go check and see what that's looking like. I think that's right. Okay, now let's drag this baby out. Awesome. Okay, so this is pretty much everything you have to do here, guys. I don't know what happened to my chart title. Okay, then you would just say this is your variation. So guys, that's about it. So overall, you're looking at your visit case should be your almost ideal one. All should start at 1. Is going to be your lowest around -3. Should return back to around 1. As I said, there was issues with that, but it is higher than our other cases that include viscosity, so we're onto the right track. Okay, you can compare the other 4 cases, and this is your plot that you're going to turn in for the project video. Okay, all right, that's about it, guys. Thank you for watching.